get captured. So yes. A few logistical updates. So as you can tell, we're back in person. Everything seems to be functional. So I will stay here as long as things keep working. If I hear that something has changed, I will let you know. Homework 3 was due yesterday, so everybody here can breathe a big sigh of relief of having turned it in, and now it's my turn to start grading. So my hope is to have those back to you within about 10 days or so, because then you would have about 10 days to turn it back around to do a revision, if need be, for any points that you may have missed. Those are up to you. If you look at your score and like, yeah, I'm happy with that, you don't have to do a revision. But if you'd like to, you can earn back any points missed for things that were not due to lateness, and that will be due on the 14th. The next thing that you have to do is formative assessment number 4, which I put up this morning. So you can get started on that now, anytime. You should have all of the information that you need to do that, and I will let you know when homework 4 is available. It's going to be another CAN data assignment, this time using the same gambling items and fitting binary and ordinal models to them using M+, and probably Levon, but I haven't double-checked everything, so I will let you know when the assignment goes up what software can be used for it. I'm optimistic that I can use both, but I can't promise that just yet. In terms of other things, I updated the printable syllabus that goes with this class, which I don't normally do, because I also changed another due date. Previously, you had homework 5 due the week of Thanksgiving, and I decided that that was just nuts, so we're going to do it after Thanksgiving. So hopefully you can turn it in ahead of time, and then you can have a week off to go visit your family or, do your laundry, whatever you want to do to celebrate Thanksgiving. I will not be going anywhere, so if you have email questions as you're still working on things during that week, that's fine. I'm not planning on having office hours, though, since it is a holiday week. And I will try to put that up reasonably soon, but basically you're going to take homework 3 and do the same thing except fitting IRT and IFA models instead. So the objective would be to see how the story changes as a function of fitting a probably more correct version of the model, because I think everybody here has some ordinal data to some degree. If ordinal data is not what you are working with, then please let me know, and I can try to help you find something or figure out a way to move forward that would still be of comparable levels of difficulty. The other thing that I wanted to mention, as I mentioned in my email, on Thursday we'll have a visitor to class. You don't need to do anything different, but that person will probably want to ask for your opinion about my teaching and your experiences at the end of class. So I will leave the room so that that can happen and then come back later. I am actually giving a talk on Thursday at the University of California Davis Quant Group at 3:30. So I will come back in here to get set up for that. But otherwise, if you want to chat with me, office hours tomorrow or email is fine with that. All right, I think that's everything that I wanted to say about that. In terms of the material that's starting to stack up, we have Lecture 5 and Example 5 to finish today, and that is my goal, is to get through what we have remaining in that, talk about estimation and the translation into limited information. In terms of Unit 6, it does not look like we're going to have time to go over 2 of the examples that I had listed. That didn't happen 2 years ago, so I'm consistent in predicting how much time we are or aren't going to have. And so I had covered these examples in previous classes, and so I have a link to where they are. They're also 6B and 6C. And then I have a number of articles that I would recommend. So the other types of responses that we can't get to in terms of examples in this class, nominal. There's one about using nominal models to include semi-ordered nominal response models for missing data or not applicable responses. And then I had example 6C is about count type outcomes. And so there's a new article that just came out that I added to that, which I had not had the reference for down below, but the article has been on your reading list. And then I added one more article that I just came across recently. This one is new, and I uploaded that into Icon. So in the readings, it's outside the folder since it's new, so you don't have to go download them all again, but that's a new one. And that will be forthcoming at the end of next month. All right, so any questions or things I'm forgetting? Yes?
So, I was trying to ask about this. If you have a Likert scale where one does not mean strongly disagree, and instead, where, I'm gonna back up.
Okay.
3 is neutral.
Okay, 3 is neutral.
And, am I saying this right? Anyway, if 1 to 5 does not mean strongly disagree to strongly agree, do you have to recode so that it's, set up from least to greatest?
Do you have to reverse code? Is that the question?
Yeah, or just like, do you have to manipulate it so that, or can you just use the scale however it's made?
I think that regardless of whether you're fitting a normal response model or an ordinal response model, more should mean the same thing with respect to the trait.
Okay, so it should line up.
Yes.
Okay.
Yes, so if a higher response, if somebody who has more of the trait should provide a higher response, like it should be consistent across all the items. If somebody who has a higher trait value should provide a lower response, then you would want to rearrange the data to make that inconsistency go away.
Okay.
Otherwise, you can have estimation problems because the model doesn't know which way is up.
Oh, I think my brain is just fried now. Because 3 would, like in a normal Likert situation, 3 would be neutral.
Not necessarily, but the ordering of it should be consistent across items.
Okay.
If a higher response goes with a higher trait value, that should be true for all the items.
Okay.
Because otherwise you don't know which direction your trait is more of the trait, or is lower score is more of the trait. Because if you have a combination of positive and negative items, then the loadings can switch. You could have positive loadings and negative loadings that would fit as well as the reverse, which would mean the trait is backwards.
And it would be like lack of.
Yeah.
Okay.
Yeah, so
Okay.
you'd be measuring sickness rather than health, for instance.
Yeah.
And so to know which way is up, everything should go in that way to start with.
Okay.
Yep, and start values can help too if there's any problems in that regard, if the data aren't strong enough to tell you which way is up. Okay, other questions? Let's see, it is October 25th. How's everybody feeling? No? I'm right there with you. In my previous class, I couldn't come up with piecewise coding to save my life on the fly. So I'm right there with you. But you know what we're going to do? We're going to get through it. One way or another, this semester will eventually be over. I know it seems like a long way, but we have made great progress. We've all learned a lot of things, right?
We should be comparing ourselves to the null model.
The null model, exactly. The null version of you did not know any of this. So that version of you, we've said goodbye to and we've moved on. There is no saturated model. We'll just say that. There is no end point because perfection is never the goal. But there is something to be said for getting this far and still being here. So thank you for that. I appreciate that. All right, let me get stuff up for you to look at on your side of the screen. That's what I was trying to do. There we go. So just to remind you, 2 different versions of these models that we're talking about, because this is a quiz question as to what these things mean. So we had, let me back up a long, long time ago, the very beginning of this unit, we talked about the way that things are described versus the way that they're estimated, and those have different names. It's not the one I want. It's related to this, though. 1 second. There's a table. Here it is. This is the table I want. Slide 20. So the combination of how these models are expressed and estimated historically is what yields the differences in naming conventions. So the examples that we've seen so far have all used full information estimation, which is a word that I've said and waved my hands about and we'll talk about in a little bit more detail today, otherwise known as marginal maximum likelihood. And if we're using that method of estimation and the way that the model is expressed, so parameterized, expressed, phrased, all of those words meaning the same type of idea, if what you have are A and B parameters, then you would call that combination of using full information estimation and getting A's and B's back that you did IRT. And in particular, the models that we're focusing on is the 2-parameter version, where each item has a different A discrimination that says how related it is to the trait, and then each item has a different B location, which gives the amount of theta needed to have a 50-50 probability of a correct response. In M+, what you get directly is the loading threshold version instead, but M+ will convert the loadings and thresholds into discriminations and difficulties for you. So the loading threshold version tells you the same thing in a different way. Loadings are slopes, just as they were in the CFA unit. It's just that we're predicting the logit or probit of the item response instead. A threshold is an intercept that's backwards. So it's a location parameter that describes what is predicted for an average person. So I say in this unit that we're doing IRT/IFA because to me they're the same thing. And which version your software happens to give you is whatever. You can get the other one if you care about it more. Personally, I like the A's and B's better than the loadings and thresholds. Where we have not seen yet is this combination down here, the idea of limited information estimation as an alternative, and in particular, the use of weighted least squares. So when you're using this method of information and you're getting loadings and thresholds directly out of your program, that is where the term IFA comes from, item factor analysis, or also CFA models for categorical data. So if someone says it like that, this is probably what they mean. There's nothing that stops you from reporting A's and B's out of limited information, in the same way that there's nothing that stops you from reporting loadings and thresholds out of full information. These are just conventions. It turns out that limited information estimation is much, much easier, much more conducive to having multiple factors, and thus is much more common in the world of structural equation models for categorical data. Traditional IRT programs, though, are going to predominantly use full information instead as their estimation option. Do you want to talk about the parameters briefly? The A's and the B's and the loadings and the thresholds and the intercepts? Oh my. Yeah, question?
So, if we have missing data, which way will be the
So the question was, what about missing data? Short answer, full information. The longer answer, full information as a term more generally means that you're using all of the original item responses to estimate the model with. And full information maximum likelihood operates under an assumption of missing at random, which means random after factoring in the data you do have for a person. So it's not completely random, it's conditionally random based on what they said for their other item responses, any covariates that you have, any other predictors in the model, that kind of stuff. Limited information, as a general term, means that you start with a summary of the data, and that summary information is what the estimator is working with. So anytime that you start by making a summary, the model doesn't know what you summarized over. So then the assumption that you're making about any missing data is missing completely at random, which is exactly what it sounds like. That there's no reason for the missingness. It has nothing to do with the predictors you do have. It has nothing to do with the outcomes you do have. It's just that. So that's the downside. If you think that that is implausible, but you need limited information estimation for other reasons, then that's where you're into like maybe a multiple imputation plus limited information kind of combo so that you address the missingness in a separate step. But that's the drawback. Good, now I don't have to cover that slide. Thank you. Yeah. One down, 90 to go. But this is the one. Let's see, Zoomers. Here we go. I didn't forget you, I swear. There we go. So I'm on slide 63 to remind us about what all the parameters mean. So 2 different versions of an item factor analysis solution where the loading is there either way. So the loading is your slope. That means it's the discrimination parameter. It means how related is your item response to the trait, where your item response is being put through the logit or probit grinder first, but it's still the item response is the outcome. if I were to plot predicted logits, then this is a linear function, the same as it was in CFA land. My term right here, the mu looking thing, that's my intercept. So when people talk about the slope-intercept form of an IRT model or an IFA model, this is what they mean, this way. So the intercept is the predicted logit when your factor score is 0. What is it the predicted logit of? A 1, because the model is predicting up. The whole model is trying to predict the logit of the odds of the probability of a 1. So this is common because people know what to do with this. And it is indeed a linear function if you're predicting the logit or the probit as the outcome. Then we get into this middle ground here with this stupid thing, which is a threshold. Thresholds tell you the predicted logit of a 0 instead for somebody who has a factor score of 0. So how do intercepts and thresholds relate to each other? Quiz question? Yeah. They're backwards. Times minus 1. If I know that the logit of a 1 is a 2, I know that the logit of a 0 is negative 2. So if you're working with M+ or any other software package that insists on thresholds, you may switch the sign and call them intercepts, and then you're back to something that people know what to do with. Why do we have thresholds? Because they go in the same conceptual direction as the B parameters from the IRT version of the model. So this would be the discrimination difficulty version of the model, or the AB version of the model, however you want to say it, where B is a location parameter that tells you how much theta you need to get to a logit of 0. Where more B means it's a more challenging item, you need more theta to get it right. So those ideas then are operationalized on this picture, as well as the conversions between the two. Let me see if I can make it a little bit bigger. There we go. So if you have a model in which your factor has a variance of 1, the conversions simplify greatly. Variance of 1, mean of 0. Then the loading is the same thing as the A. So in this picture showing an item characteristic curve, which is showing how theta as the predictor on the x-axis is creating an expected probability of an item response of 1 on the y-axis. The slope of the line at a probability of 0.5, that is 4.3 in this picture. So 4.3, my slope, that is how much the logit of the item response is expected to increase for a 1 standard deviation increase in theta. And it's in logits, which is why it's so big. So that would be just a straight slope if the y-axis were logits or probits. It's a bendy slope here, but it's the slope at that point, which is what I've tried to color in here. So that one's relatively easy. You get the same thing either way. If you have a model in which theta variance is something other than 1, then that goes into the denominator. Now the other two, red versus blue. I like blue. That's the B version. So the difficulty value is the amount of the trait needed to hit the 50-50 mark in probability. So it's how much x do you need to have a y of 0, where a logit of 0 is 50-50 probability. So that is the location on x that corresponds to y of 0 in logit or probit metric. The red part here is the intercept instead, which tells you what y would be when x is 0. So the difference between difficulty and intercept, difficulty tells you how much x you need to get to y equals 0. Intercept tells you how much y is if x is 0. So they're both relative to something being 0, but it's a different point, x or y. And so then the intercept for this item is 1.69 in logits. That is the expected logit of a correct response for somebody who has an x of 0, theta of 0, And if I unlogit that back into probability, what's the technical term of unlogit?
Inverse link.
Inverse link, there we go. I like unlogit better, but you know, you can't write that in a paper. People will laugh at you. At least not pre-tenure. So if I unlogit this back into probability, that's a probability of 0.84, which is right here. So intercepts tell you for the average person, what's your probability of success on this item? If an intercept tells you the probability of success, a threshold tells you the probability of failure. What's the probability of a 0 response instead? It's minus 1.6, or a probability of 0.16. So thresholds and B's go in the same direction. That's probably where that came from. But to put it in the linear model, you do have the negative out in front, because this term should have been predicting the probability of a 1 instead, to be internally consistent.
Lisa, can you explain that again when you said thresholds and B's are in the same direction?
Yes. Thresholds and B's are both indicators in which higher values indicate a more difficult item. So a B that's higher says you need a higher theta to have a good chance of getting this right. A threshold that is higher means you have a greater chance of getting this wrong, which is another way of saying it's a more difficult item.
Okay.
Yeah, intercepts are higher is easier, because intercept is the probability of a 1. So an item with a higher intercept has more likely to get it right. That's an easier item.
Okay, so in both of them, higher is more difficult.
In thresholds and B's, higher is more difficult. In intercepts, higher is easier.
Got it.
Just like it was in CFA.
Got it. Thank you.
Yep. So then what you report, I think, depends on who you're talking to. If you're writing to people who are used to seeing confirmatory factor models and structural equation models, I'd give them intercepts and loadings. If you're writing to people who are used to seeing IRT models, I'd give them A's and B's. If you're not sure who you're talking to, make a table with all three. Or maybe put some of them in a table and put the rest in a picture. You know, it's up to you. If reviewer 3 says that IRT and IFA are not the same thing, show them these formulas. And there are a number of places that you can cite. The earliest one, I think, was probably the late 70s or early 80s, initially came up with this correspondence. The exact correspondence depends on how it's parameterized in your software, but the M+ manual for IRT models will tell you all of the different permutations. The ones that I'm using go with something called a theta parameterization, which we have not talked about, but we're going to. Okay. How are we doing? Yes, it's confusing. But it's just different ways of describing the same phenomenon, came out of different traditions for different purposes. Nope, not ready to go yet. Can we be done yet? No, Lisa, we cannot be done yet. We had to figure out where the numbers come from and why there's no fit. So everything else that I have to say is agnostic as to what type of the model that you're talking about. The question is, how do we come up with these numbers in the first place? And why is there a distinction between limited information and full information that wasn't a thing when we talked about this in the context of CFA models? I have a few other slides just trying to make the point that if you have a link function, you can model it. So there's nothing that stops you from fitting these kinds of generalized latent variable measurement models to any kind of outcome. Count outcomes, zero inflated outcomes, beta distributed outcomes, whatever you can think of. If there's a link function for it, you can fit it in here somehow. They just don't have special names at that point. Okay. Last piece of this then, just to make a point also in relation to your quiz, the idea of reliability. So do we have omega anymore in these models? or some easy to get one number that summarizes reliability. No. Would it even make sense if we did?
No.
Yeah, I say no. Some people have, that's a thing that some people have put forth, and they put it in a logit metric, so it sort of makes sense, but to me it misses the point. Why not? Why doesn't it make sense in these models to have one number that we call reliability?
Because the mean is a function, or variance is a function of the mean.
Yes.
Because we have,
No sum scores. Is that what you said? Even if we had sum scores, they would have differential reliability.
the thing is that we have different levels of information across different theta
Yeah.
values, so we cannot assume that only one value will describe the entire distribution.
Exactly. The reason is this bendy line right here. Each item is only effective at discriminating people of different thetas within its difficulty range. So the amount of reliability you have depends on how many items you have at each point along this theta continuum and how discriminating they are at that point. So information and reliability necessarily vary in any kind of latent trait model where the relationship between the trait and the item response is non-constant. If it's nonlinear, then the item has to shut off. That means that certain items are going to work better at certain ranges of the X trait. So that was where we had information functions in example 5, for instance, that looked, in my example, like this. So this is page 4 of example 5, very briefly. I had 7 items that were indicators of the degree to which an older adult can live independently, essentially, is the latent trait. And all of these items have item characteristic curves that max out in terms of predicted probability well below a theta range that would be plausible in terms of high ability. They stop around theta of 0. So none of these items can distinguish people of above average theta values. Consequently, the test information that they create tanks because there's nothing that we can say about the people who can do everything. We don't know how much ability they have because we can't measure it. They can do all the things we asked. And test information is a quantity that most people will probably not know what to do with. We can convert it into a traditional metric of reliability, information over information plus 1, and that same picture looks like this if you change the y-axis to reliability. So we can then describe over what range of the trait would we say reliability is acceptable. Or you define maybe what acceptable is, like if I want to say 0.8, then I'd say that I have adequate measurement of my trait up until theta of, I don't know, 0.2-ish or so. And after that, reliability is no longer sufficient. That information function then leads to this giant pile of people. These are all the people that can do everything. We don't have any way to sort them out. So if I were to try and describe the reliability of this instrument, I don't know how I could average across. I basically have none for these people, but good reliability for these people without distorting the story. So it's reliability for whom? For what level of the trait? That's the big difference. In CFA, it's just assumed to be constant, even though it's probably not. All right. Questions or comments about that much? Everyone's writing. I think that's a good sign. Either that or you're like, I'm so bored in this class. My son has to keep a journal at school, and that's what he writes in his journal, is how much he hates school and wishes he were home playing Nintendo. So I'm not going to check your journals. You can write whatever you'd like in the privacy of your own notes, but I feel like it's good if you're writing something down, because maybe I said something that, mattered for once, that wasn't in the 90 slides. Who knows? Dare to dream, Lisa, dare to dream. All right, want to talk about estimation? Said no one ever, but I got to do it a little bit. So I'm on the end of the set here, slide 67. Okay. So estimation in these models is a lot trickier than what it was in CFA. That's the big picture. Now, more of the details here. So in terms of estimation, we're using maximum likelihood, which means we have a distinction in which parameters are considered fixed versus random. That's one of the main differences in between adding the Bayesian component, is that everything becomes random. But in this context, we're saying that item parameters are treated as fixed effects, meaning that if I have item 1's A, and item 2's A, and item 3's A, those are three separate numbers. I'm not trying to make any inferences about any other items, like I just want to know about that item. And so the goal is a number that is the most likely estimate of that discrimination, as well as a standard error that tells us the expected inconsistency of that estimate across repeated samples. The people, though, the thetas, they are random effects in the model, they are not. So even though theta is in the model equation as a parameter, we don't know or need to know what theta is for person 1, what theta is for person 2. That's not something we find. All we need to know is their distribution. So if we say that theta is supposed to have a normal distribution, then we know the means, variances, covariances if there's multiple thetas. That's what we work with. We can ask for predicted thetas after the fact, but they are predictions, not model parameters per se, in this method of estimation. In Susan's IRT book, I think I assigned the estimation chapters to that. She discusses some of the older methods that tend not to be used as much. So conditional maximum likelihood you may have heard of before in IRT class. Is that a thing? Yeah, that's for Roche models, where basically you treat the sum score as if it were theta. Joint maximum likelihood treats all the thetas as if they're fixed effects, which is not good because then the more people you have, the more parameters you have to estimate, which is not how it's supposed to work. So what we're focusing on then in terms of the gold standard within maximum likelihood land is what's known as marginal maximum likelihood, also known as numeric integration. So this is what we've been using in M+. The reason that I have not shown corresponding examples in Lavaan yet is because Lavaan doesn't have this. You would have to switch to a different package that does full information maximum likelihood for these models. They rely on two assumptions of independence. So after you control for theta, or however many thetas you have, the responses are supposed to be independent, and people are supposed to be independent as well. If neither of those is true, then we have to change the model to make it work differently. So we don't need to know the individual thetas, but we do need their distribution in order for this to work. Let me see. Yeah. So here are the steps, basically, that would be happening under the hood when you hit run in M+ or what other programs. We start with start values for all the item parameters, and those can be computed in logit metric, but just using classical test theory. So what is the probability of a 1 across people? Well, let's just take the item mean, convert that into logits, and that's a good starting point, for instance. We have to compute a likelihood per person given the current values of the item parameters for the fixed effects. So what do we currently think item 1's A is, item 1's B is, and so forth? And then we have to deal with the fact that we don't know what theta is. That idea that we don't know theta, but we're going to try out potential values, is where we get into the concept of integration, which is the idea of somehow trying to find the area under a curve. It's a more general term. In this context, the term that you will see is either the terms numeric integration or Gaussian quadrature. Quadrature is the key word here. So if you look through your program's documentation and you're trying to figure out what kind of estimation it uses, if you see any of those keywords, then it's using marginal maximum likelihood. The key idea is that we're going to try on a whole bunch of different potential theta values, see what the likelihood would be under each, and then add them up in a weighted way based on how likely each potential try is, and that becomes our summary of each person's contribution to the likelihood. I've got some tables on that, but that's the big picture idea. And it keeps iterating until the overall likelihood doesn't change, at which point it decides that it's done. How it goes about trying on new values depends on what's operating under the hood. Calculus is used in some cases, an EM algorithm in others, and that's more information than I care to present in this class. But here's the basic picture. What we're trying to do is select however many thetas it would take to approximate this overall distribution. So this is my attempt at describing quadrature, which is the idea of rectangling this distribution so that we can sum up the rectangles and get an approximation of the area. The number of rectangles is the number of quadrature points. More is better, more takes longer. M+, for instance, defaults to 15. Some IRT packages I've seen default to 30. So one of the reasons that you may get different answers across packages is how many quadrature points you're using. The idea of adaptive quadrature means that it goes through this process twice. It first rectangles the entire distribution, and then when it figures out where a section the person is going to be most likely to be, it re-rectangles that section. And this is why estimation becomes problematic when you have multiple thetas, is because for each distribution, or each dimension, you'd have your own set of rectangles. So let me give you a real-world story. The weather is turning colder, and one of the reasons why I don't like colder weather is because I have to put pants on. I hate pants. I'd prefer to be in shorts at all times. And the pants that I've settled on are basically yoga pants with, like, you know, the pockets to make it look like they're dress pants, like the cheaty pants. The type of pants I hate the most are jeans. No jeans ever fit me, and they're super uncomfortable. But everyone, like, wears them, so I feel compelled to own jeans. The other reason I don't like jeans and pants is because the size that you are depends entirely on the manufacturer and what store you're in, and the numbers are just, like, irrelevant. Right, so men generally have it easy because at least your pants come in 2 dimensions, right? You have a length and a width, and like women's pants, it's like 8. Like, how much is that? I don't know, less than 10, more than 6? Like, it doesn't have any, you know, relation to inches or centimeters or any kind of physical measurement. So I already hate trying on pants, but if I'm going to try to find a pair of jeans that fits, it's like I have to find a range of the numbers. And then you have potentially a range of the widths or manufacturers or styles. So it's like, just picture, like when you think of M+, like churning through these things and it's taking forever, like picture me going into the dressing room and trying on all these different pairs of pants. And then what if I want to not have like boot cut pants? What if I, God forbid, want to try on skinny jeans? All right, then I have all the numbers plus all that dimension of type too. And so then it's like a 6 in skinny jeans might not be a 6 in boot cut. So I have to cover all my bases. So that's what goes through my head, at least when I think about this, is this process of like trying on multiple iterations of all this stuff because I don't know what size I am and I don't know what style is going to work for me. And that's why I just wear shorts or mom pants all the time, the end of the story. But what's happening under the hood would look something like this. Trying on jeans M+ style. So let's say that I have a model in which I have 2 items here. So item 1 has a mean of 0.73 in terms of its probability of a 1. That corresponds to a logit of 1, so that's my starting value for this item's difficulty. Let's say that I'm fitting a Roche model to make my math work easier, in which A is 1 for both of these items. Item 2 is a harder item, so its starting logit is, or mean is 0.27, logit of -1. So its starting value is going to be positive 1 instead. Cool. So then for any one person, I got to try on potential thetas. Because I don't know what their theta is. I don't know what kind of pants I wear. We got to figure it out the hard way by trying on. Well, if I say that theta has a mean of 0 and a variance of 1, then these are some plausible values I could try on for my theta. I could say, well, maybe I have a theta of -2. Maybe I have a theta of 0. Maybe I have a theta of 2. So this would be like 3 quadrature points instead of 15 or 30 or however many. Here's my model equation. Okay, so if my best guess for my current item parameter for number 1 is a B of -1, and my current guess for my theta is -2, Then -2 minus a -1 gives me a predicted logit of -1. That translates into a probability of a correct response of 0.27 or a probability of an incorrect response of 0.73. Now I know which actually happened. I know if I got the answer right or not. So I know which of these should be relevant. Let's say that I got the answer right, so the 0.27 is relevant. Now for the second item, my try-on theta is still at -2. -2 minus 1 gives me a logit of -3. The probability of getting the answer right is 0.05 if I only have a theta of -2. Probability of getting it wrong is 0.95. If I didn't get it wrong, this one's irrelevant. So if I multiply these two probabilities together, then here's my likelihood of getting both of them right if my theta is -2. Okay, with me so far? Now, how likely is a theta of -2? In a normal distribution, is that pretty likely? No, it's kind of out in the tail, right? Like it's 2.5% or something, right out there that way. So I'm going to downweight this try-on value. Like, okay, well, this is what it would be if theta is -2, but -2 isn't that likely. So I'm dividing up the area into these three rectangles. I have an area of only 5% for this section. It's a width of 2. So here's 10%, 10%, here's 80% for the middle. So I multiply then that value by the probability that I have a theta of -2, and then there's my result. I do the same thing trying on a theta of 0 instead. Here are my probabilities of a 1. If theta is 0, here's my new likelihood, much higher. That theta of 0 itself is much more likely, so the end result is larger. How about a theta of +2? Just as unlikely as a theta of -2 in a normal distribution. So here's my likelihood. The fact that I got both of these right means that it's probably more likely that I have a theta of +2 than 0 or -2. But theta of +2 is not that likely. So then my end result is this one. And then I sum these numbers together, and I get that one. And everyone's like, oh my God, stop talking. So just picture this try-on process. At every step of trying to figure out what A and B is, each person has to try on 15 thetas. Figure out what the likelihood is of their item response pattern if that were their theta, figure out how likely that theta would have been, and then add together all of those combinations to come up with one number that describes their data. So we're integrating over the unknown theta by trying on a bunch of different values for it and seeing what the likelihood would be for each of those potential tries. Now, what if I had a model that has 2 thetas in it? Could I do that? Yeah, I can. It would be complicated, but instead of having 15 tries, that's for one theta, 15 tries for the other, how many is that?
15 times 15.
225. Now what if I add a third theta? I need like another arm to go into this dimension. I think it's 725. I think I looked this up once. It's a lot though. 15 to the third power. Can anyone tell me?
That seems low.
Is it low? 725 sticks in my mind, but I could be completely making shit up.
3375.
Okay. 3375 it is. 725 must have been from some other random number that's stuck in my head. How do we decide the theta probability is a question. It comes from the normal distribution. So basically, how many rectangles do you have? How much area under the curve would each of them cover? And that's the weight that would be attributed to that try-on in terms of how likely that theta is to happen. So this process starts to fall apart when you have multiple thetas in the model because of this try-on process.
It sounds Bayesian.
It sounds Bayesian?
Yeah.
Kinda, maybe. I think it's a lot closer. But the reason that we have to do this is because there is no formal distribution that takes Bernoulli item responses and multivariate normal thetas and can like stick it together into a closed form. My students have tried to name it before. I like the ones Bernoulli or Bernoulli. There is no Bernoulli or Bernoulli distribution. And so this is what we're stuck with, is integration. But yeah, I think this is, I mean, this idea of resampling and trying on and seeing what it is and seeing what it is, like, it is getting into that kind of like a chain kind of idea. But that is why, at least in psychometric models, Bayesian estimation, I think, is relatively more prominent than in other fields, is because this sucks. And that's a viable alternative that allows you to not have to integrate. It can be faster and it can be more accurate, and then you have more control over what the rest of the model would look like. So this is a laborious process, basically. Once you have some item parameters, then you can figure out what theta could be for each person as a prediction using the same type of thing. So a few slides of this based on a thing in Susan's book. I'm going to skip over these for right now because it uses calculus to figure out for each person whether it's headed in the right direction. And first derivative to know which direction should be next, second derivative to figure out how fast you get there. So the end result of this then is that we don't have thetas for each person, but you can predict them. However, we have to remember that theta comes with a prediction error. Like the numbers that you get out, like F-scores or whatever, like that's the mean or the mode or some other measure of central tendency of a distribution. So we want to try to keep the error with the factor scores if we take them out of the analysis and try to do things with them at other places. The whole logic of structural equation modeling, though, is that we don't have to take them out. We can treat them as latent variables without actually having to turn them into scores of any kind. 3 different methods of scoring that you'll come across. ML can't be used for perfect response patterns, and so we end up adding stuff to it based on the idea of a prior distribution as to what theta is supposed to be. So yes, now we're solidly into Bayes territory. These are the 2 that you will come across, EAP or MAP. EAP is what we want. MAP is what you get out of limited information. So in your homework and in the example that I have, I would go through the process potentially of using limited information to see if the model fits, but then once I have something I'm happy with, re-estimate it using full information, maximum likelihood, so that I could get better factor scores if I wanted to go and use those descriptively or otherwise. But EAP is what the keyword that we would use to describe what comes out as a prediction. We've done this one before, the idea that if you're in marginal maximum likelihood, you get likelihood, you can do differences in likelihood. I didn't do MLR for these models, although I could have. The reason for it, the R part in maximum likelihood estimation with the robust part, that's for deviations of multivariate non-normality of the item responses. So in CFA, that's potentially a concern. In these models, that's not a concern because we're not saying the responses are normal. We're saying they're ordinal or binary. Question?
So when I was looking at my results for homework 3, they had RMSEA, and they had standard and robust, and then they underneath that had another thing called robust RMSEA. So what are the differences between all that?
The robust one is the correction to the fit statistics and standard errors for deviations of multivariate non-normality. Ender's chapter 5 will describe that better than I can.
Okay.
The second set I've only seen in R, and I'm not honestly sure what they're correcting for.
Okay.
That's a relatively new development that's come out within the last couple of years.
Okay.
So it's like doubly robust, which implies that it's a different kind of robust. It might have to do with sample sizes. It would be my next guess as to what they would want to correct for, because that's usually the next thing, is to prevent small sample bias. But you'd have to track that down and figure it out. Since it's not an M+, I haven't made that a point yet. But yeah. So what we've seen thus far in example 5 is using marginal maximum likelihood. So estimator equals ML link equals logit. You can choose logits or probits if you have that. But then in terms of model fit, this was all we got. So we have AIC, BIC, and log likelihood, but we don't have the magical H1 model to compare against, which means we don't have all the other fit measures. We also don't have a null model to compare against, which means we don't have those fit measures. So what would we do instead? There are local fit measures that are tedious at best to look through when we're in marginal maximum likelihood. Tech10 is the option that I have given on your example. What it does is print a list of every pairwise crosstab for every pair of items. And it gives you the observed versus expected frequencies, and you get a chi-square test for whether observed and expected match, where expected is based on the model and observed is based on the actual data. And you're supposed to scroll through all of these to figure out what your local misfit is. So it's not ideal, for sure. There are a bunch of newer measures that are using full information maximum likelihood as an estimator, but then trying to summarize them with limited information statistics. So I have there's an article about this on your reading list written by this person, Albert Maidu Oliveris. He has a bunch of stuff on it that I've linked to from this page. And some of this newer stuff is available in R. Not in Lavon per se, but in R more generally. It's not yet enveloped in M+. The lack of global fit comes from what the saturated model would have been and why it's not something that we can use. So in regular flavor maximum likelihood, there is no covariance matrix that we're trying to come back to because binary items and ordinal items can't be described that way. You're missing some information. The saturated model, what it would be the full response pattern that is given by the number of responses to each item, then exponentiate, or is that right? To the power of? Is that the right word? Thank you. Yeah. To the power of number of items. So for instance, in your homework, you will have 24 items measuring gambling behavior, each with either starting with a two response format. That creates a contingency table of 16 million and some odd responses, potential cells. So that would be the thing we'd compare against. So we'd have to have our observed contingency table of every possible response pattern versus the expected from the model, and the mismatch between the two would be our indication of fit, but that's not going to work. I don't have 16 million people, and most of the time, not even Nikki has 16 million people, I bet, in your data set.
Nope,
No, and
I topped out of 4,000.
yeah, and the EPLS program has some of the largest data sets I've seen, but you don't have 16 million, you're not going to get a good measure of fit. So this idea of what is the rightest answer is all possible patterns is not going to work in most cases. And that's what we saw in here. This was an example with only 7 items, and we couldn't even fill up 630 cells in the table. So I've only seen that even be possible a few times if you have a ton of people and very few items. So then, what do you do instead is switch estimators. Yes?
So, in what situations the model fit globally and doesn't fit locally, and the vice versa?
Okay, say the first part of that again. In which situation?
Yeah, the model fits globally, but doesn't fit locally or local fit.
I would say that
Relative.
we can do relative fit.
Yeah.
We can always do -2 log likelihood differences. Like if we would have a model that's a 1 parameter model versus 2 versus 3, we can always do that. But there's no direct way against the total response pattern to say this fits like adequately. Like absolute fit as the rightest answer is not a thing. Because there's no way to summarize that many response patterns and compare it to a predicted response pattern because there's too many.
I'm thinking that from the assumptions of IRT that it is like a sample independent or invariant. So in this case, for these specific sample, items cannot fit with all population unless you applied those items for the 16 million people to that sample. Am I right?
It's not even about the assumption of person independence. I would say local independence is closer. There's nothing, in example 5, for instance, I did a comparison to see whether we should have a 2PL or a 1PL. That's a relative comparison, and we went with 2PL because it fit better. There's nothing in here that tells me whether these 7 items actually measure one thing and one thing only. We don't have anything that says the expected response pattern is sufficiently consistent with the data response pattern where they match, in the same way that we have an H1 model versus an HO model that is sufficiently consistent. So that's what we don't know, is absolute fit. We only know relative fit. Am I answering your question, or am I just talking? Okay, I'm trying.
Thank you.
Yeah, I may just be talking, but I am trying. Yeah, again, this is not my wheelhouse. But I understand the limitations, though. Like, functionally speaking, I can't test it very well in this sort of way, which is why there's a different game in town. All right, so the other game in town, then. This thing, limited information. So limited information as estimated using some flavor of weighted least squares. There's a bunch of different ones. The one that is sort of the current one that everybody uses the most is called WLS-MV and M+. The rest of the world calls it diagonally weighted least squares. So if you see DWLS, that is the same thing. The key idea is that, well, if we can't summarize, in this case it was 630 cells in the latent class table, why don't we just start with this? Why don't we just start with my tetrachoric matrix and work on that? That's the idea. So rather than try to recreate all possible response patterns, the estimator is trying to recreate this tetrachoric correlation matrix. That's my H1 model. That's my saturated model. Now I'm back in business with respect to everything that we did for FIT and CFA. So this becomes the answer key. The weighted part has to do with the priority of each of these estimates over each other. If I look at the standard errors of these tetrachoric correlations, one of them jumps out at me as pretty bad. The standard error for the correlation between 4 and 7 is much higher. And the reason for that is because there was an empty cell in that cross tabulation where everybody who said that they could shop also could already answer the phone. So they had to add a tiny little number just to even get a tetrachoric correlation estimate, but they don't really know how good of an estimate that is. It's not very good. So the estimation process then is going to emphasize recovery of the correlations that are estimated better relative to the ones that are estimated less well. That's the weighting part. And we're only working with 2, what's the word I want? The second moment is close to that. We're trying to recreate the overall probabilities of 1s and 0s. We're trying to recreate the second order, basically, correlations, but we're not trying to do anything past that. We're not trying to recreate like a 3-way contingency table, 4-way, 5-way, all the way up to that. So it's limited in the fact that we've summarized the most important part, but that we're leaving some of it behind. So this is where that picture comes from, which I had decided to do earlier. The mean and variance part then corrects the difference in what this ending up chi-square is of your predicted matrix versus the data matrix. After re-emphasizing some of the correlations more than others, it's not chi-square distributed. So the MV part tries to fix that, the consequences of the weighting. Yes?
When did this come out? Like, this method?
Oh, boy. Weighted least squares has been a long time.
Okay.
It's related, I think the history of this was the ADF estimator for asymptotic distribution free. I want to say Michael Brown or Rod McDonald or both in like the 80s was a solution to CFA for non-normal data, and I think they kind of hacked that idea into this.
Has there been anything better that's come along since then?
What I would say is, I think what ends up happening is there are some routines that use marginal maximum likelihood to find the parameters. But then to evaluate fit, they switch to this kind of limited information approach, where they would try to figure out the extent to which, like the tetracork correlation model that is predicted, the correlation matrix that's predicted by the model would be consistent with some other one. The problem is, like, how do you get to the saturated model? That's actually Jihong's dissertation, who just graduated yesterday, so if you see him, he is now Dr. Zhang. But that was what his dissertation was about, is how is using Bayes nets to come up with the saturated model that you would compare alternative psychometric models against.
Okay.
So this idea of tetracork as a way to indicate fit, I think, has traction. That's a relatively newer thing. But you'd have to go through, like, I would say read this guy's stuff, like the history of IRT fit, and summarizing the sort of the first order moments, making sure you get the probabilities right, and the second order would be the correlations, and then they basically skip everything past that, the second order. But it's
What would be the third order?
the third order, I don't think there's a way to describe it in terms of covariances, but it would be like a three-way contingency table
Okay.
rather than just two-way. This is analogous to two-way.
Okay, so it's like adding another way each time you go.
Adding another moment, so like in normal data, like if it's actually normal, then you don't have any skewness and your kurtosis is 3. But if it's not normal, then you have skewness and your kurtosis is some other number than 3. This is kind of like in categorical data, there is skewness in kurtosis. There's like stuff that's past the correlations. I don't have the right.
Extra parameters you have to keep including.
There's extra ways two variables can be related if they're categorical,
Okay.
and it's easier to think about that in terms of contingency tables than the word covariance or moment.
That makes sense.
Ask Jonathan, please.
Yeah.
My head hurts from hitting the ceiling of what I've learned, because we're right at the ceiling of what I can do to
Okay.
explain this,
No,
if
but
I'm being real.
like the whole like I remember going over those things, and that is now making more sense. So
Yeah, it's chi-square tables is sort of like is the way that you can think about it. It's like your model should make it so that for any pair of items, the observed and expected crosstabs should match.
okay.
And are you going to check at that level, or are you going to check at the level of like 3 items at once or 4 items at once, all the way up to as many items as you have? That's the saturated model end point. And you need 16 million people to like even get that, let alone check it for 24 items. Did you have a question? No? Are you going to help me with my poor head?
My head also.
Yeah, my head hurts. I'm being real, folks. Like, I've had conversations with a few of you over email about this, but it's like the world of quant is a very big tent. And to be able to be a quantitative methodologist and do it well, you have to understand theory, you have to understand programming, you have to understand how it's applied to data to answer questions, and you have to understand how to explain it to people. The people who don't want to learn it but should. Like, why would they want to do this? And to reach those audiences. And each of us sort of gravitates towards the part of that we like the best and we feel like we're the best equipped to do. And I am definitely on the further like translation application side. And I don't have the technical background or interest, to be honest, to explain this with any more detail than I can. Because I just don't care. It bores the shit out of me.
Yeah.
And that's someone else's job, is the way that I look at it, right? And those people don't want to deal with data or talk to other folks, and I do. So it's,
I can understand that.
and you all are supposed to do all of it to some extent, so good luck. But I'm here to tell you that it's okay if you don't understand everything. Reading is going to help, practice is going to help, and yeah. How's that? Yeah?
Lisa, so in this case, we will start with the polychoric or tetrachoric correlation metrics. Then we will take the probit the probit of that, and then we will calculate the covariance metrics.
Tetracork is kind of already in probits.
Okay.
Yeah, that's like the way that I think about it is like, it's like if you could convert your data into probits and get the correlation among the probits, like that's what the tetracork is trying to give you. That's not quite correct, because at an individual level, it's either a 0 or a 1, and it's not a probit, but like as a
Yeah.
summary across people.
Okay.
So it's already in the right metric, and then basically you just estimate the thresholds and loadings that would be consistent, that would try to best recreate that tetrachoric matrix is the right answer.
Okay.
So it works the same way as it does in CFA at that point,
Yeah.
which means that then you get all the regular things. So once you have that, then, let me fast forward a minute. This is the end of example 5. If I switch these two things right here, estimator goes WLSMV, and then there's two choices for the scaling of it. Parameterization equals theta is the version that corresponds to probit, so that's why we do that one. Then all of the fit information looks exactly like it used to. It's back. Because we have an H1 model now. We have the right answer for what the data want the tetrachoric correlations to be. We have what the model says it should look like based on the patterns of loadings and thresholds. Error variances are constrained to 1 for identification in this model. We don't have those, but we have factor variances and covariances as well. And so we get a chi-square test of model fit that is the HO versus H1. But what we don't get is log likelihood, because that's not how it worked. There's no likelihood involved. But that's conceptually what the same chi-square test of model fit is in WLSMV land. There is, yeah, we're going to run out of time for this. We'll do this next time. There is a downside, though. Here's the point buried on slide 85 that you asked me about earlier, missing data. Anytime you operate on a summary, missing is completely at random. If you're working with individual responses in maximum likelihood, it's at random instead. So it boils down to like which is more important to you, essentially. Marginal maximum likelihood is going to give you probably the better estimates because it's based on all the original data. It has a more realistic assumption about any missing data, but it's going to be very difficult in models that have a lot of factors. So if you want to do a structural equation model and you have categorical outcomes, WLSMV is probably what you're going to end up with. Or Bayes, as it were, but that's a lot harder. The other thing is that in WLSMV, everything is in probits and not logits. So in the WLSMV parameterization, something has to be 1 as a scaling factor to nail it down because we're dealing with imaginary underlying variables. And so you can either say that the total variance of each item is 1, or you can say that the error variance is 1. Error variance is 1 is consistent with the probit parameterization of IRT. That's the theta version. So that's why I'm using that one in the examples. So in the code, everything is exactly the same except for this right here. And I've added one more thing that's also different. This is another thing that you don't have to type, but I do it for completeness. Error variances are fixed to 1. They have to be. The next unit that we have after ordinal data is invariance. And when we get to these models in invariance, this could potentially be not 1 at a later step in the testing. But for now, it's 1. So loadings all estimated. Thresholds all estimated. That's what $1 means. It's the first threshold for each of these items. There is only 1 threshold as of right now. Error variances are fixed to 1 for identification. And then the factor variance is 1 and the factor mean is 0. So now we have chi-square test of model fit. Says not great. What do you think about the others? Yeah. So this is, RMSEA says, not terrible.
We have 99 earlier.
Yeah, they're really happy with it. So I will tell you there is a lot less research on what is good for these cutoff values in this world than there is in CFA world. And that's a continuing area of development as to how do our standards for what good is need to change for categorical data, and how do they even need to change as a function of, say, how many response categories you have. It turns out that it's easier to find good fit if you have, I think, fewer response categories than more, if I remember correctly. But it's an active area of research. So if you're looking for dissertation topics, that would be one potentially to consider. So we get these values. We're not exactly sure how to use them, but at least it's a lot easier than trying to come up with 16 million people to fill out our contingency table, relatively speaking. We'll talk about model comparisons next time, since it's 3:14. All right. Any last minute questions before I send you on your way? All right. Thanks for hanging in there. I hope to see everybody Thursday, and we will finish this and start ordinal. Woohoo. No, the good news, there's nothing new to learn. You already know how to do ordinal. Seriously. The only new idea is submodel. And if you had generalized before, you know what submodel means. That's it.
The thresholds for thresholds.
It is, do you remember ordinal data and generalized?
Yeah.